So today we're going to look at, discuss the difference between we'll do a quick review and then discuss the differences between the open and closed basin wetlands, which is an important concept in terms of planning water developments and also assigning risk to the ponds. And then we'll talk about what relationship we're using in regards to the pond surface area and volume to predict the risk. Talk about some of the current model assumptions and the challenges, as well as look into how to address some of those challenges by using the flow accumulation model and using that in terms of trying to predict these open and closed basin wetlands. And I have at the end that we'll look at accessing the different map layers, but I think we're going to move that to webinar 3, and we'll start or finish webinar 3 with that point, just because I'm just not sure we'll have enough time to get through that today. So we finished off Tuesday with an overview of the 8 maps that are put together that kind of complete the surface water risk assessment set. I've got it listed as forage and water resilience set here, but it's the same sort of project concepts, I guess. And so we have the reference evaporation, the Beck maps, the slope, the forage categories, the flow accumulation and the disturbance history, and these are the sets of maps that we would, and then another map that would be used for, that we can use for range management, which would include either an orthophoto or some fence lines and stuff like that. So yeah, you're seeing 7 maps there. The disturbance map is missing off of that slide, but then there's also one for that has the range management layers on it as well. So how do we assess risk to these different ponds? And the model that we're using to build the maps assigns risk based on assumptions, just like every I guess every GIS model does. You know, we don't have an endless supply of ground truthing done for some of this stuff, and so we have to make a few assumptions. And however, the overall theme is that as it gets hotter and drier, there'll be more evaporation and more demand on surface water, and so that drives the main assumptions. And risk is mostly associated with ponds that are closed basin versus ponds that have access to groundwater flow. And so we'll go through what some of that hydrology looks like and kind of what some of those ponds look like on the landscape. So the first step of this assessment is to identify the resource, the water resource, and then try and come up with an assessment of how it's at risk. So first, if we look at the reference evaporation maps, we can see the change in reference evaporation on the landscape, and then this is like our starting point for trying to predict the zones of use. And for now, the risk assessment is based on pond size. And the ponds that are at risk are highlighted in red. So there's the red circle kind of on the bottom right of this map. And whereas ponds that are considered resilient are highlighted with the green line around them. And so the buffer is a 1.5 kilometer buffer. And that's the assumed distance that livestock will travel on this landscape in a more complicated or complex topographical landscape. And so this makes the assumption that the pond size, so the ponds that are circled in green are then greater than 5 hectares, and the ponds circled in red are greater than 2 hectares and less than 5 hectares. And the concept is that if we're planning according to climate change scenarios, then we should consider only those water sources that livestock have access to high quality water as potential locations for future use. And if we're discussing the potential of arrangement for livestock grazing, then having an understanding of where the surface water is and which is reliable and where it's located can help determine things from potential carrying capacity to our infrastructure needs in terms of, you know, where is water short on the landscape, potentially where our fences is going to get more pressure, you know, maybe where trail systems are needed and things like that. So this information can be used for a number of different infrastructure needs. some range units have been under the same management for many, many years, and the producers and managers likely have a far more detailed understanding of where the livestock are and what they're using and what the model can predict. However, in areas where there's new management or where there's multiple uses or other agencies that are interested and maybe don't have that same knowledge base of livestock use and the likelihood of livestock using a specific area, the maps provide a good starting point for those planning purposes. And so this is just like a close-up, more of a close-up representation of what's available. So once the ponds are identified as resilient or not resilient, we assign a buffer, and so like I mentioned before, that buffer is this 1.5 kilometer radius around the pond, but we can also use a 3 kilometer buffer depending on the landscape, really. Like if it's a less complex landscape, then we will provide a 3 kilometer buffer around that water body and assign a zone of use that's a little bit larger. Each pond has a unique identifier, and so you can see that highlighted here, that each one of the ponds has a unique name or a unique number associated with it, and that number comes into play when we look at the evolution of the pond through the grazing season. And so each one of those identifiers is tracked can be tracked with a spreadsheet. And the ponds that are identified outside of these buffers, those are ponds that are less than 2 hectares. So they're kind of considered always at risk. And that may or may not be the case depending on whether they are connected to a water table or not. So continuing on with the assumptions, where this concept of risk comes from? Typically, so grassland ponds operate as a closed system, and they don't have, depending on, but they can be characterized as not having a lot of input or output from other surface water sources. And the way to think of this in BC systems is like our grassland ecosystems with less slope variation, so like less than 10% slope variability over the landscape is so relatively simple topography. This is kind of the case for those ponds, and there's little input from the groundwater because the groundwater table in some of these systems can be quite far below where the pond basin is, and so then that's why we're not getting that input of groundwater. In all of these, this equation at the bottom, the volume is associated with groundwater inputs and groundwater outputs. Yes, it is, but in the smaller ponds and in grassland systems, generally we lose that groundwater part of the equation. So the relationship between surface area and the volume can be thought of using this equation where, so it's based on a regression for a whole bunch of ponds that were sampled, like hundreds of ponds that were sampled in grassland ecosystems in sort of the, I guess, like Saskatchewan, Manitoba, through the northern Great Plains of the States. And so there's a lot of data that drives this equation, and it's a fairly strong relationship, the volume versus the area of the pond in smaller wetlands and smaller ponds and smaller lakes. So those less than 7 hectares, there's a very strong relationship. But once we get over the size of 7 hectare ponds, that relationship starts to fall apart. And so we have less ability to predict the change in area and change in volume with those larger ponds. And so that's another reason why we're kind of keeping with that that sort of 2 to 5 hectare size, and because we have a little bit more certainty that the change in area and change in volume that's associated with evaporation can be better predicted in the smaller ponds. And an improvement to this would be like to be able to create do a basin analysis on each pond, so create a bathymetric map on each pond, and this can be done. There's been like a lot of improvements in just recreational sonar through the fishing communities, that can be done at an individual level for a range unit if it's really truly if we want to even further improve this relationship. But for now, we're pretty comfortable with this regression that we have, or that we're using. So what that looks like when I'm talking about the evolution of a pond through the grazing season, and when I'm talking about this relationship of surface area to volume, what we can get for each pond now that we have this unique identifier is we can have this calculation of pond area and how the pond changes through the season. And so if we know what our pond full area is based on our GIS layer or a trim layer, or you could even base it on a walk around the pond with a GPS unit and get an area of a pond and then plug it into this equation. And so our volume is based on that area and that equation in the regression. And then we also have our precipitation inputs, because that's a direct input to the water budget. And then we have our reference evaporation that's out. And then at the end of each month, we get our water balance, which provides us with the amount of evaporation that's happened, and then that information can drive the next equation, which is, okay, based on that evaporation, we have this much less surface area, and therefore we have this much less volume. And as you track it through the season, we assigned a pond to be at risk if more than 50% of the area of it disappeared through the grazing season, or more than 50% of the volume disappeared through the season. And what that works out to is that, so if a pond is about 4.5 hectares in size, it reduces to about 2.5 hectares in size by the end of the grazing season. And its volume, if we're looking at around 18,000 cubic meters, it drops down to about 9,000 cubic meters through the grazing season. And so this change is considered to be a large risk for those ponds less than 5 hectares. Once they're over 5 hectares, you start getting into changes of that 40%, 30% range in terms of the area to volume ratios. And so you can kind of look at this on the landscape, but you can kind of observe your high water marks at the start of the spring. The water in some of these closed basin ponds is at the shoreline, and then as the pond evolves to the grazing season, the water shrinks, or like the surface area shrinks off, and then you end up getting muddy and rocky banks and just an overall reduction in the water. So those closed basin ponds, this is sort of what they would look like. And we'll get into the connected ponds here soon, but they're a little bit different. But overall, that's if we're looking at a risk to livestock water source, we're considering what's happening in terms of like a function of the pond through the grazing season. And so in terms of livestock use and implications for livestock, then that leads to some of the stuff we discussed in the previous webinar around poor access, which can mean less time for animals out actually feeding. That they're spending more time searching for water. This can affect health, especially if it's quite hot out. It can also affect health in terms of the water quality, and it can reduce weight gains and things like that. So there's lots of livestock, actual like specific livestock management reasons why we want to know which ponds are at risk. And it also can provide information for water developments if we're looking at some more simplified water developments like point access. How much of the shoreline is being reduced through the grazing season, and how far out do we need to lay some sort of good footing, like whether it's geotextile or gravel beds or something to lay out so that the animals can get into the water enough to actually drink, or get into the pond enough to actually drink without having muddy footing. That's an important information to know in terms of designing water developments, as well as understanding where water quantity is and water quality is. We also, outside of, I mean, not outside of the realm of livestock, but we also have implications for pond ecology and ecosystem services that we need to consider. And these are things that range management, the part of our objectives of range management are to maintain these ecosystem services and ecosystem values, and knowing which ponds are most at risk helps with the overall management of the range. And smaller ponds are more susceptible to damage if overused. They're valuable in terms of what they contribute to carbon storage, water storage, primary productions, and all kinds of this, like a plethora of research has been done on temporary waters and the ecological role that these small wetlands play on our landscape. And so understanding the impacts of climate change and water budgets and how these are going to change in the future, it's not just information that's useful for range management, but it's information that's useful for just ecosystem management in general. And I guess also a little bit of a response to the question from Tuesday around water developments limit evaporation. If we look at these photos on the left and on the right, things that limit evaporation are generally anything that can reduce wind, reduce solar radiation, and reduce temperature, since those are the primary drivers of evaporation, and maintaining the vegetation along the edges of these these smaller ponds can limit the evaporation just by reducing the wind and creating some shading and things like that. So yeah, acknowledging that which ponds are at risk is an important aspect of. So on the range unit scale, then we have this reference evaporation map with our unique identifiers and our spreadsheet that's associated with each pond. And then the reference evaporation map, when we overlay it, it provides a good representation of which ponds on the landscape have the most evaporative demand compared to other ones. And so it's just a simple visual. And then once we know the risks of these ponds, then we have these zones of use maps, again, just as a review. And the map on the right has just the 1.5 kilometer buffer, whereas the map on the left has the full 3 kilometer buffer. So we can see where our predicted zones of use are based on resiliency, with the 2 to 5 hectare lakes are represented in the far left diagram. The greater than 5 hectare lakes are represented in the middle diagram. And then just as a contrasting way to demonstrate you can use the red or the green lines as well. So we have a couple of ways that we can look at these maps if we want to. So the summary of the assumptions: which water sources are at risk? Ponds greater than 5 hectares likely have a higher volume and are resilient, and also by their size, they're more likely connected to the groundwater. And the ponds that are 2 to 5 are likely at risk in future climate scenarios, whereas ponds that are less than 2 hectares are probably always at risk to evaporation and to just general evaporation that's used throughout the season. And this is for drier ecotypes. So again, once we get into the more the wetter ecotypes and wetter ecosystems, we don't have as much evaporation. And so the 2 to 5 for the caribou, this is a very important, I guess, pond size. Now, the challenge that we've met now is this connected ponds, and while our evaporation estimate is based on surface area, the impacts of evaporation on pond size and area are not predictable in connected ponds. And our regression is specific for closed basin. And so how do we address this challenge of trying to identify where the connected ponds are on the landscape? And that's probably the biggest challenge of the model right now. And we want to identify at this desktop level, where are these connected ponds, and also trying to capture all the other water locations that livestock use in the landscape to incorporate that into the zones of use map, whether it's point access along a stream or an existing water development. We need to start bringing those in. And so over the next few slides here, we'll kind of go through some of the strategies to try and create that more, that truer range or livestock use zones of use map. And so there's been some previous work on just looking at how to do a field assessment or a quick questionnaire to determine connected versus closed basin ponds. And so Climate and Agriculture Initiative, previously the Climate Action Initiative, provided this document that's available on their website as well. And so it will go through a questionnaire in terms of like looking at the hydrology and the vegetation of a specific spot. And that can help assist with identifying a closed versus a connected pond. And so some of what I'll go through here is also associated with this document. And if we look at what is a connected pond and the general hydrology of wetlands, connected ponds have this input from either groundwater or through flow of water through them. And so in a situation characterized by it's connected to the groundwater where it's providing input to the groundwater, but these are generally larger ponds that have a lot of pressure on them that are able to push water into the groundwater flow, whereas lots of our grassland ponds and the smaller ponds are more characteristic with B, where they might be connected to the groundwater by able to provide input to it, but more likely they are kind of very closed in terms of just getting precipitation input and also overland flow from spring freshet, and very little is disappearing to the groundwater system. Oftentimes these also have that clay pan that I mentioned last time at the bottom of them, from the finer particles being carried through the water solution into the bottom and then settling at the bottom, creating this clay pan. And so that also prevents water from going into the groundwater system. And so we need to acknowledge, in order to like, I guess, model this, we need to acknowledge that the hydrology is complex and not try to over model, I guess, just like base our predictions on what we know and don't try to overstep the reaches of the model. So there's complex hydrology that's associated with the wetlands. And so what we need to do is find, simplify the model and then find a way of identifying basically what's connected and what's not connected, and then that will form the basis of our predictions. And so different from the closed basin pond, the connected pond has this input from groundwater and output of groundwater generally. So we've simplified it, or what we want to do is simplify the wetlands that livestock use as being either connected or perched. And so perched is our closed basin and connected is our connected. And you know, generally there's important aspects of being able to distinguish these, and one of them is that if we're developing water and we need to create water developments, we need to know whether it's a perched or a connected pond, because that can really influence the type of development that we use. Those closed basin ponds aren't recharging through the grazing season, and so they can be more at risk to water quality issues. Whereas ponds that are connected, generally we don't have water quality issues with that, so we can get rid of that one big concern of water quality if we can identify that ponds are connected. And yeah, that's probably all I need to go through there. Looking at them on the landscape, the challenge or the risk of perched ponds is that they tend to they will dry down. And so looking for salts and mineral content on the soil surface often is a good indication that the pond is perched. Either it's drawing minerals from the groundwater and evaporating them off, or there's minerals associated with the actual surface water that are drying off and being deposited on the soil surface. Vegetation is quite different. We get this more saline tolerant plant communities that are associated with perched ponds versus connected ponds that are more associated with things like sedges and willow rings, aspen, things like that are just as broad categories of vegetation types. And you know, with determining how to develop these ponds, you can probably get away with scoop outs in connected ponds, whereas in perched ponds, like I mentioned before, you can't get away with the scoop out method. So it's important. It's an important aspect of water development planning to be able to consider these. So once it's all said and done, we have our model with our assumptions on it. we have our closed basin ponds identified by size, but in reality, we need a map that reflects this resilience of the connected ponds. And as all these ponds are accessible by livestock and important sources of drinking water, we need to know which, we need to, I guess, create a new map that has this buffer that acknowledges those connected ponds. At a range unit scale, we can do this with that climate change impact risk assessment tool. Your local knowledge of your water resources, discussions with producers as to where livestock are watering. Those are all important aspects of determining which ponds in the landscape are resilient and which ponds aren't. And so, just like as an example, discussions with producers, just asking the question around, you know, which ponds are drying down in drought years versus which ones aren't, can actually go a long way in just telling us which ponds are closed versus open, as well as like a vegetation assessment on them can tell us whether a pond is closed or open. And there's another thing that we're working on at the desktop level, which is the flow accumulation model, and that can assist with showing where water is moving on the landscape and which ponds are connected to other ponds and which ones are completely isolated from the water, the groundwater influence or surface water on the landscape. And so I'll pass it over to Darren to discuss how the flow accumulation model is put together, and then I'll come back and sort of just summarize how we're using it in terms of range management and helping identify the ponds and helping identify potential water locations. Darren, can I pass it along?
Cool. Yeah, you bet. You don't mind driving the slideshow?
Betcha. Okay,
awesome. Okay, so flow accumulation is really one of the moving parts in the bigger machine of watershed development, watershed building or basin and sub-basin building. And I guess the first thing to note really is that the flow and flow accumulation is a bit deceiving. It's a bit of a misnomer because it doesn't really measure the literal flow of water. It measures the theoretical flow of water along a modeled surface. So even without water of any kind, digital water in our model, we can still visualize and quantify the direction water will flow. And then we can also quantify where that water would accumulate. And all we have to do is really hold two important assumptions. And one is that water always flows downhill and water always flows in the steepest direction. If we hold those two assumptions, the flow accumulation model works fine. I want to just, next slide. So if we look at a starting point for flow accumulation, it always starts with a digital elevation model. Remember when we were kids and we put a whole bunch of chairs in the living room and throw a blanket on top of those chairs, and some of the pointy bits stick up and some they're sagging in other areas. That's just really our wireframe or our digital elevation model. And what we do is we assume that if we poured water on this modeled surface, it would flow from the red and orange areas through the yellow, down through the green, and then finally accumulate in the blue areas, taking that's the steepest route possible to get to the blue areas. But it's important to note with this, for instance, that this is really exaggerated STM just for illustration purposes. The surface doesn't have to be this dramatic to model flow accumulation. And in fact, flow accumulation becomes way more useful when the surface topography is less dramatic and a little more subtle. Go ahead there, Andrew. Okay, so first we need to establish the direction that water will flow. And I know this looks really geeky and nerdy, but we'll just walk through it. It's not that difficult really. So we need to know which direction the water is going to flow. So if we squish or flatten that digital elevation model that we just looked at, we get this grid of evenly spaced cells, and each cell has an elevation number associated with it. And each cell can only have one elevation number associated with it. So the algorithm just examines this elevation value assigned to each grid cell across the entire surface, and flow direction is just derived using something called a D8 model, which is down at the bottom there. So essentially what it's just saying is that water can only flow in one of 8 directions out of a cell. The directions indicated by an integer between 1 and 128, as you can see. And remember that water is always taking the steepest route between numbers. So if we look at the cell on the far left, 4 down there, 4 spaces down, you see an elevation of 64. 64 can only flow in a couple of directions. It can either flow to 69 above it, 53, 58, 61, or 68. Those are the only directions that can flow out of that cell. So if we look for the steepest decline or the largest difference in elevation between 64 and its surrounding cells, we see that the biggest difference in elevation is between 64 and 58. So the cell flows, in air quotes, in the upper right direction. And if we look at the D8 model, we see a movement in the upper right direction is represented by the integer 128. So if you look at the corresponding grid next to it, you see that that cell that used to be called 64 is now called 128, because that's the movement or the direction that that cell is flowing. And this process is conducted now for every cell on the surface. So it goes through the whole thing and does that for absolutely every cell. Okay, the next slide there, Andrew. And then we end up with this.
Darren, before you go on, there is a question just on that previous slide.
Oh, yeah.
Around why doesn't it flow to 53?
It does flow to 53. Did I not say 53? Go back one, sir. Sorry, Andrew.
Do you want to just run through that quick example one more time?
Sorry, it goes to 53. I'm sorry, not 58, because it's moving in the 128 direction. I'm sorry. I misspoke. I'm sorry.
Thanks for clarifying.
Yeah, thanks for the question. Okay, next slide. So then we end up with this layer that depicts the directions that each cell is flowing to. So now we have an idea of which way cells flow. Now we need to establish that accumulation of the flow. So if you want to go next slide. Or counting the number of cumulative times an individual cell has cells flowing into it. So if we look at the cell to the right of those red dots, we can see that there's 3 cells flowing into that cell, indicated by the 3 red dots. So next slide. That gives that cell an accumulation of 3. So go to the next slide. So if we look at the cell to the immediate right of that, we see that there's actually those 3 cells plus more cells contributing to that cell. So it's not only the cells adjacent to it, but it's also the cells that feed the cells that are adjacent to it. So next slide. We'd see that that cell has a flow accumulation of 7, and so on. So next slide. This becomes really important because now we've got this layer of grids of cells that all have a number associated with them, an accumulation number. And this becomes really important because, next slide, we can now trace the direction accumulation of the water, in quotation marks, the flow, and this can be used to classify stream geomorphology or stream locations. So extremely high accumulation values indicate channels or streams that are flowing and always hold water. Medium to high accumulation will indicate intermittent streams that may only have water during or post precipitation events. And most interesting to this anyway, so the work that Andrew and I are doing, is low to medium accumulation will indicate wetter draws, or that may or may not have flowing water in them. You may not physically see the water, but they share riparian characteristics and they may support hydrophilic vegetation. So we'll look at Raven Lake really quickly as a quick study, case study to look at this. So next slide there, Andrew. So Raven Lake is a range unit, about 51,000 hectare range unit in the Caribou-Chilcotin Resource District. Next slide. And the digital elevation model indicates, if we look at that, we place the DEM underneath our range unit. We see that it has some relief inside the range unit, and it's bordered by 2 fairly large water features. So the Chilcotin River to the south, and then connected through Risky Creek, the Fraser River to the east. Go ahead, next slide. So trim water, I'm assuming everyone is familiar with 1 to 20,000 trim water, shows that Raven Lake has what looks like a mixture of both connected ponds and wetlands or perched water bodies, what Andrew was talking about earlier. So connected water and unconnected water. So if you go next slide, if we zoom in a little bit, we'll zoom into a very small portion of the southern part of Raven Lake. We can see that there's a couple of systems there that have streams or water that's connected by either ponds or by wetlands down at the bottom. And we also see that we've got a few orphaned ponds or wetlands or these perched water bodies up above it. So that's when we look at trim water, because that's all that's been identified digitally. So as far as we're concerned, those look like they're orphan ponds and they're not connected to anything. If you go next slide, Andrew. But if we look at the flow accumulation at the same area, we see that the hydrological connections that weren't necessarily visible on the air photos and therefore made it transferred over to the trim actually are exposed now using the flow accumulation. So in this example, the red lines indicate the low accumulation. The yellow are low to medium, orange indicates medium to high, and the green indicate high accumulation. So it's really the orange and the green ones that really sort of capture our attention. So next slide there, Andrew. So if you see side by side, a couple of those lines, actually particularly the green lines, are connecting some of these water bodies that aren't necessarily visible either through air photos or through trim, but it is visible by modeling that flow accumulation. And what's important is, next slide, Andrew, is that they may be exposing some significant riparian features that are holding water or indicate some sort of connection between areas of water on the landscape. Now, Andrew's much more qualified than me to help draw some inferences and conclusions about how these play a role in water development forage, but hopefully this was clear enough to show you that there are ways to see these connections between water bodies and water features that aren't necessarily evident using trim or using air photos.
So the flow accumulation, and I guess like part of the reason why we spent a little more time on this is that the intent is that it's going to start, we can incorporate this into water development planning, and taking this information can help us with like identify the landscape elements and help us with predictions as to where water could be. And one thing I guess to take that we've taken out of this is that not all landscapes, like if we have green lines, red lines, and yellow lines, not all landscapes operate in the same way in terms of what those red, yellow, and green lines mean. But if we're looking at a map and we're trying to plan water development, we have a location where there's green flow lines that seem suitable when we're out there looking at it, versus an area that has red flow lines that also looks suitable when we're out doing our field assessment of it. Understanding that the location with the green flow lines has theoretically more water coming through it and is likely a more resilient location to develop water. And so it's a planning tool that can assist with making decisions on a landscape at a landscape level. So we wouldn't take like a green line and compare it from Raven Lake and compare it to a green line in Okanagan, but we can take a green line and a red line from Raven Lake and compare them together. If that makes yeah, I think that makes sense. And so every landscape is different in terms of the accumulation of these flow points, and we find that when looking at steeper, more complex topography, that the trim and the flow accumulation line up fairly well. But like Darren had mentioned, on these less complex landscapes, the flow accumulation really demonstrates a difference in what we're seeing. And to best sort of describe that is so Raven Lake at that area that Darren was showing, that smaller section in the south, in a very similar location to that, looking at the red lines that don't show up on trim as being riparian, but on the flow accumulation they do. What we see is we see this, you can see kind of cattails showing up a little bit in this photo, as well as this, the ground cover on this was all liverworts and associated with hydrophilic vegetation or vegetation that's associated with moisture. And so knowing this can assist with calculating forage, as well as potentially finding locations in what we think of a drier portion of the landscape as potential for maybe water storage or a small water development. And so this can also come into play with the uplands function checklist that for doing range assessment procedures, where one of the questions is seep springs and ephemeral drainages supporting vigorous stands of phytophytic plants, so plants that like their feet in moisture. And when conducting these assessments, experience has been that like that this is often a question that we have questions with when we're looking like whereabouts on the land, whereabouts on our upland are we looking for a vigorous stand of plants that like their roots in a little bit of water, and so completing your upland assessment and also including these areas where these red flow lines show up can be one of those things that where this is useful, where this flow accumulation model is useful, or the map when the map comes up. And so it can also help with ground truthing, or I guess desktop truthing the model. We can look at, if you look at the ponds that I have circled in orange, they're smaller ponds, but they're lower down on the watershed, and they have flow through them. And so potentially these are locations that would be resilient, even though the model has identified them as not resilient, but because of their size, but perhaps because the rest of the landscape is flowing through them, that they're resilient. And same with one in the top right, there's quite a lot of water that's flowing through this point in the green circle in the top right. And it's not identified as a resilient water source in the model, but it is potentially a good location to look to determine if the model is true, or to add a buffer around there. To try and verify whether something's closed basin, well, the red buffer in the bottom right is identified as an at-risk wetland, and we can see by the flow accumulation lines that it's at the top of a watershed, and the TRIM can also provide some of that information, but the flow accumulation can provide it with a little bit more certainty that is a closed basin, truly a closed basin pond, and that our model is likely correct for that wetland. So we would verify our buffer and our water resources by identifying, based on our knowledge, identifying ponds or watering points that are reliable. So we create this overall zones of use map with a number of, not just with the model, but also by including the local knowledge, this flow accumulation, and assessments of whether we have closed or open basin ponds. And then this is the information. So this would be the fine, I guess for the purposes of this conversation, this is our final zones of use map. And then this is the information that we carry forward into webinar 3, where we look at now how do we bring in the other layers in terms of the forage resource layer, and calculate our forage based on the landscape. How do we identify locations that are best for completing range health assessments? How do we identify locations that have high potential for a water development? And then that will lead into the case studies in webinar 4. So next week we're going to go through an actual a zones of use map, and then calculate. We'll go through the spreadsheet that's used for calculating carrying capacity and calculating water use on the landscape. I think maybe I even have a slide. So linking that forage resource and resilient water bodies, predicting the zones of use, and then the potential uses of the mapping resources. So this is for calculating carrying capacity, water developments, potential conflict areas with cut blocks, we bring cut block layer in, private land layers. It can be used for species at risk planning and recreation and all those things. So we do have a bit of time for questions, and I'll put in. I'll also briefly mention the layers. So accessing the layers for different range units. Darren is going to go through that, I believe, at the end of webinar 3 and possibly the start of webinar 4, depending on how we're doing for time. Shauna, were you interested in running the Q&A?
Yeah, absolutely. So if people have questions, you can either pop them into the Q&A box, or you can raise your hand and we can unmute you and you can ask your question directly to Andrew. We do have plenty of time for questions, so don't be shy. Yes, there was a lot of information that came at you the last hour, but I'm sure there's a few questions out there. Okay, we've got our first one. Thank you for kicking it off. How is the planning of water developments discussed with water stewardship staff with respect to allocated water?
Right. So in terms of the model, and in terms of bringing the information to the front, like to the discussions, we can use the zones of use and the forage maps that's associated with calculating carrying capacity to determine how much water is required on any given polygon or any given zone of use. That information can be taken to the water steward. That information is taken to the water stewardships. Could be taken to the water stewardship in order to express how much water is used off of a specific location, and that we will calculate with the spreadsheet in webinar 3, where we go through and determine how much forage is associated with a zone of use, and then so we know how many animals are supported by that, and then how much water is necessary to support that forage resource. And so that can drive some of the conversation, as well as the connectedness through the landscape. So if there's certain water bodies that are known by stewardship to be of high value, or certain watersheds that are high value, we can see how the water resources are connected to that point of interest. And so I hope that helped with that question.
Yeah, thanks for clarifying that. So going back a bit to the flow accumulation model, could you just give a quick recap on what the difference is between the red, yellow, and green flow routes?
Oh, yeah. Yeah, you want me to take this, Andrew?
Yeah.
Sure.
Yeah, I think I probably flew through that a little bit too quickly. Sorry about that. So like Andrew said, it's the flow accumulation values are relative to, well, most importantly, the size of the watershed or the size of the range unit. So the bigger it is, the more opportunity cells have to flow into each other, the higher your flow accumulation numbers are going to be, right? So it's just a matter of how many cells there are. So what we're working on now is to find a way to separate the difference between the low to medium, medium to high, and high. So those different colors represented categories of 0 to low, low to medium, medium to high, and high. And remember, that's all relative to the range unit. So something that's 0 to 100,000 for one range unit is not necessarily the same as 0 to 100,000 to another one, because another one could be actually 0 to 500,000. So right now we're working with the model to determine the best way to separate that into those 4 different categories of 0 to low, low to medium, medium to high, and high. Did that answer your question?
Yeah, I think that was good answered. Yes, you received
Okay.
it. Thanks. So I think you nailed it. Andrew and maybe Darren as well. Have you guys been able to use aquifer mapping at all in doing this work?
We haven't, and it's I think if we're, yeah, I think it definitely would have potential.
And there's a question about how widely this type of water planning method is being used right now. For example, is it being used for getting water licenses, or is this still in the research phase of using this approach?
This is still in the research phase of the approach. However, like the information, yeah. So especially like the flow accumulation stuff is definitely preliminary. Like we have we've looked at maps all over the province with flow accumulation, and we can to get input for how they look, we can provide them. However, it is very much preliminary, and yeah. So the first case study that we've looked at is Raven Lake, and that's one of the pilot projects that's in the Caribou. And so you know, it's really the first range unit that we've used it for planning purposes.
Thanks. Here's a question on sort of broader implications. So is there a way to use these models to take into account the disturbance of logging or wildfire? Or is it too complicated to add in those other types of variables?
It's not too complicated at all. It's like, and it is. So the forage, so there is a disturbance layer that's brought into the maps that will show us fire from, right now we have it at 0 to 10 years and then greater than 10 years, but the fire will, but that's might not be fine enough fire. And we also have the age of cutoffs that we bring in. And so we know, especially, you know, some landscapes, we know that the forage resource after harvesting can fluctuate from, you know, we can have a decent forage resource after harvesting up to maybe 15 years, and then the cut blocks become so ingrown that they're not accessible anymore. And so that type of analysis can also be brought into this, as well as what's happening after fire. And you know, we have a loss of forage for a couple of years, but then we probably have a flush of forage for many years, depending on what happens after, in terms of what management comes to, whether it gets planted with trees or not, how long that forage resource is potentially there. And so that information can be brought in spatially to look at, and then it's kind of, some of it would be up to the manager to determine how to use it, but the information, the location of where things are is there. And then how the forage resource changes in time with cut blocks, we have some of that information that can be available. I think we have less information in terms of how the forage resource changes with fire.
Thanks. We do have several more questions that have been typed in, but I'm going to go to a couple of people who have raised their hands to ask questions. So Connie Haley, if you would like to unmute yourself, you could ask your question.
Can you hear me?
Yep.
Okay. Hi, Andrew.
Hi,
I just have a couple questions for out here in the Chilcotin, because of course, like Elephant Hill, we burnt so substantially that it's changed the hydrology quite substantially. Like I'm looking right now on my other screen at Raven Lake, which has flooded the entire Raven Lake Road in many, many places. So you do your homework, but yet the number of years, like this is probably our third year, I think, going into this crazy fluctuations of where the hydrology has changed substantially from our 15 years of drought. How do you incorporate any of your ground truthing when now everything's underwater? It's kind of like, because I know we've done a lot of water developments out here, but and some of them being in that Raven unit, it looks like you're doing a lot of homework there. But now that everything's changed so drastically with the big fire, it's kind of a segue from that last question. I'm just wondering how you do homework on those big changes, because Raven Lake looks nothing like I've ever remembered it looking like in 25 years of being here. So just a question.
I kind of think time will tell in a sense as to what's going to happen to some of that hydro. I guess it would be the same, some of the same analysis as after the mountain pine beetle, all the mountain pine beetle harvesting happened, and how it changes. You know, there's lots of, I guess, anecdotal and real information as to what was happening with the hydrology. But I think the flow accumulation can help with that. It can show where the potential points for flooding are in the landscape, or where the potential higher zones of moisture can be predicted after, if we take away that buffer of the vegetation and take away the you know, the shading from the trees, and we create, you know, increased runoff and maybe higher rates of runoff, then I think the flow accumulation can start to assist with that information as well, at least represented on the landscape where those points are, those points of accumulation or points of concern could be. I don't think I can answer much more than that though, Connie, sorry.
No, that's good. It's just all so different.
Clayton, do you want to go ahead and ask your question?
Yeah, sure. You guys can hear me?
Yep.
Yeah, so actually it's not a question. I just wanted to step in and speak more to that water allocation question. We're in a status quo position with water licensing at this point. There was a lot of work done over the past number of years to move a livestock water regulation forward. And currently that has not gone forward, and it may or may not in the coming years here. So we do still require water licenses to do our water developments. If we're talking about fully allocated, the livestock have been on the land for decades or even centuries in parts of the province, and they've always been using the water. That should have been part of an allocation budget on those systems. So, you know, we do still need to do planning with our water allocation staff, but the provision for water should still be there for livestock on the land. So it's just a matter of working with your district program staff.
Yeah, thanks for jumping in there, Clayton, with that additional info. We do have a few more questions, and so I'd love it if we could stay on. It is 9:30 though, so if people have to jump off, we will hope to see you next week on Tuesday and Thursday again. Yeah, but we'll just go through the next couple of questions. So this one might be for Darren.
Shauna, before you go on with that question, Shauna, sorry, can I just address something that Connie said really super quick?
Oh, sure.
Just for you to do that. So Connie, we can also create what's called sinks with the flow accumulation as well. So if you have an idea of how much flooding is going to happen, so if you can estimate or predict that, then we can also then add that to the flow accumulation, and then model where this sinks or where the water will pool or where the water will flood. So we can also visualize that as well.
Great, thanks.
Yeah, thanks for that additional point. So Darren, I think this one will be for you as well. What time of year would you ideally do the flow accumulation assessment? During snowmelt or during a drier period? Is there a better time to do it?
Again, it's a bit of a misnomer because really it has nothing to do with water as much as it has to do with the surface, the ground surface and the topography, right? So it's not necessarily relevant if there's lots of water or not any water there. It's a theoretical surface that if there was water there, this is where it would flow or most likely to flow. So you can certainly add variables to your flow accumulation model to predict how much water, but that won't necessarily change which direction the water will flow or where it will accumulate, because that's all part of the digital elevation model, not necessarily the water itself.
So if we look at the season, the season won't necessarily matter, because we should still be able to tell if the vegetation is influenced by more wetter conditions or more water, and we should also be able to tell if we're dealing with an intermittent stream versus a perennial stream, and so even though there might be actual flowing water present in a spring assessment and not in a fall assessment, the characteristics of the landscape, like just the stream geomorphology of the intermittent streams, we should be able to tell that there was an intermittent stream there, as well as we will still be able to identify riparian vegetation. So in terms of total volume of water, we won't be able to tell that without an actual, like, a measurement of the water moving through the system. But in terms of the influence that water has on the landscape characteristics that we're most interested with, or that we are interested with, that should be able to be done at any time of the season. Like ideally, we'd look at Raven Lake and say anything that shows a red line is riparian vegetation. Anything that shows a yellow line is an intermittent stream. Anything that shows a green line is a perennial stream. And so for that range unit, we want a cutoff of the red to be riparian vegetation. And I think, and then that helps with a number of management questions.
Great. So we just have two final questions to wrap up. One of the questions is, do you think that establishing the flow accumulation can affect the agricultural productivity of arable land? And this is coming from someone who's doing a PhD looking at the impact of climate change on winter wheat and maize.
Well, I guess it would, like, So I have a lot of experience with grain farming, and like what I would, the flow accumulation might assist with showing where, maybe showing where a field will be more productive versus less productive, or showing where nutrients are moving, or where, yeah, I'm not entirely sure at that scale how useful it could be. Like at a field scale, it's more of a landscape type analysis. I see it more of a landscape type analysis, but let me think about that, and if I come up with anything, I'll let you know on Tuesday.
Great. And the final question I have for you, Andrew, is around any potential negative impacts for water development in relation to ecological needs. Is that something that people need to be considering? And maybe this is sort of a segue to next week's sessions.
Yeah, I think that's extremely important, and it should be at the front of our minds when we're planning water developments. And the purpose of the water developments, purpose of planning water developments is to mitigate some of the negative impacts that livestock can have on these water sources. And it is definitely, it's always front and center in my mind when I'm looking at water resources. And I think for many people it is front and center. So we will discuss how the developments in the Caribou, or how the pilot projects address some of the ecological concerns as well, and how we're monitoring that.
Great. Well, thanks so much. Thank you everyone for those excellent questions, and to Andrew and Darren for sharing your knowledge and experience and staying on a little bit longer. Yeah, so Andrew, do you want to just give a final wrap up?
Sure. See you on Tuesday. I hope that, yeah, I think in terms of actual like range management planning, the webinar 3 and 4 are going to be now focused on that. And so we've moved on now from the climate models and the flow accumulation model to the actual planning aspects of things. And yeah, looking forward to Tuesday.
Great. Thanks so much. See everyone next week.